Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Okay, so let's get started. Hello, everyone. It's my pleasure to introduce Tianqi and Eric from the University of Washington. Even though they are still students, but they are working on a very cool project, a deep learning toolkit, a very powerful deep learning toolkit in the open source world called mxnet. And for your information, Tianqi is also the main author of another very popular open source machine learning package called XGBoost for gradient boosted trees learning. So welcome Tianqi and Eric to MSR to give a talk on mxnet.
Okay, thanks Ken for the introduction. It's a great pleasure to give a talk here. So today we are going to mainly talk about mxnet, the insights that we learn from the system, and mainly what the system, the motivation that why we designed it. And Eric is going to talk about some tutorials on usage and advanced use cases. So first, I'm going to acknowledge our collaborators, including contributors. Especially we got two Microsoft contributors here. Chuntao is from Microsoft Research, and Tianjun, who is sitting on the audience. He is now in Microsoft Bing image team, and they joined us in the very beginning. And if you have questions related to internal stuff, you are more than welcome to ask them if I'm not appropriate to answer. But so yeah, and we also want to thank Jacob for proposing the bucketing API, which is used for the language understanding and comes very handy recently. So this is the outline of the talk. And today we're going to talk about deep learning systems. And as you know, there are a lot of recent deep learning frameworks. Each come with their own unique features. Ken had a very nice survey about advantage and disadvantage of all these systems. Well, mxnet is not yet in one of them. Hopefully it will be. And today I'm going to talk about, I want to discuss in a very different perspective. So all the existing surveys about this system ask the question like, what are the nice features of all these systems in the current stage? So let's ask a different question. So let's ask, how will this system evolve and eventually become, given the full engineering power and all the things that you can throw into it? Because different systems provide different user interfaces, and different user interfaces will eventually lead to the limit in their capabilities. These are like boons in those systems, and the operators, all those engineering efforts are like meats in the system. So these boons will eventually result in what's the limit you can achieve, and in terms of flexibility and the power of those systems. So today I'm going to talk about from this perspective. So I'm going to talk about programming models. So normally, if you think about deep learning or any programming or any task in machine learning, you need to program them, and that's the interface you have. There are two types of programming models that you can use. One type of programming model is called imperative programming. So here, this is the imperative programming of NumPy script that gives you the result of E here, which is a very simple result. This is not yet deep learning, but as you all know, that Microsoft has a toolkit called CNTK, that's computational network toolkit. And Google have another famous framework called TensorFlow that all of these operates on those computational graphs. And bear with me, this is the basic task that a deep learning toolkit need to be able to do efficiently. So what imperative programming does is that what you do is that you will implement all those operations like matrix multiplication in neural networks. There will be more complicated things like convolution and element-wise addition. And the imperative program will do those things step by step. So you write your program. As you execute this clause, it will basically translate into a kernel call on GPU or some CPU functions. On the other hand, another more typical way is actually in most deep learning platforms is called declarative programming. So in declarative programming, what you do is you first declare those computations you want, and then you send those computational graphs to some compile function or other equivalents of compile function. Then you can utilize those compiled functions for your result. So the difference from the imperative programming is that in the declarative programming, normally you first declare all you need. Then the computation only happens after you do the compilations. A typical example about declarative programming outside of deep learning context is SQL for database, which I think many of you might be familiar with. So many of the existing deep learning frameworks also usually use those declarative programming. For example, if you think about configuration file-based frameworks like Caffe or CNTK, you declare networks. That's basically the declarative part. In other frameworks like TensorFlow or Cyano, you use the Python API. That's not very different from a configuration file, but more flexible. But it gives you a more flexible way of declaring what those computations you need. So, what are the difference between the imperative programming and declarative programming in the context of deep learning? So think about deep neural networks. Here, this is actually a shared neural network. What declarative programming gives you is actually a black box. So usually you declare what other computational graphs are. Here, this is the one layer neural network. Then you throw it to the toolkit and tell the toolkit, give me the gradient and give me the output. And the toolkit is able to give you whatever you require. On the other hand, if you do imperative programming, you need to write the script layer by layer. Basically, here you have some functions called layer 1.forward, layer 2.forward, then you call backpropagation. Of course, in some popular systems, they will do the wrapping for you, so that for example, in Torch, you can build all those configurations, and the imperative part is actually hidden in the code. But you can always dig into the code and hack them if you are a good hacker or researcher, because for any of the advanced need you need. So these are two programming styles. What are the differences? So one of the advantage I'm trying to argue for declarative programming first is because most of our frameworks follow the declarative programming paradigm, including all the frameworks you see except for Torch, I guess, in the deep learning world. So the declarative program are more efficient, mainly because they are allowed to do more optimization, because you don't need to specify what procedure you need, but instead you only say what you need. So take this for example. So assume that we want to do these calculation steps. The left side is the imperative program, and right side is a declarative program. How many bytes you need to finish the calculation, basically in a Python console? So in the left side, you can see that there are 4 variables here. And each of variable takes 10, 64-bit float. So normally it would take like four times the array time. Four number of arrays to finish this calculation. On the other hand, if you do have a declarative program, what you can do is we can find that the declarative program will find that C and D can actually share the memory, because C is an intermediate memory that isn't seen by the user. So you can kind of optimize out and get 3 copies of memory instead of 4 copies of memory. This might be a very naive example, but it's kind of demonstrate that the difference between declarative and imperative. Because in the imperative world, you specify the calculation procedure, and that might not be optimum. And another key property about this is that the imperative program need to be prepared for all the possible futures. Say that you are writing this program in a Python console. When you write to this point, actually the imperative program doesn't know that whether C will be used in the future or not. So it can not actually directly reuse memory. Of course, the Python garbage collector can kind of reuse them if it gets recycled. But this is somewhat limited in the sense of deep learning, which we'll give a more detailed example in the next slide. So on the other hand, in the declarative part, when you do the compilations, the declarative program sees the entire computational graph, as well as the boundaries. By boundary, I mean that the program can see what are the input and output, and what are the intermediate stages. And all these intermediate stages cannot be seen by the user, which means that they can be freely optimized out, be rewritten, or doing the memory optimization that we mentioned earlier. So a more realistic example in the deep learning world is that it's about this case study about what's the memory cost you need to run an n-layer neural network if you only want to do a prediction in a production environment instead of training. If you do an imperative programming style model, if you do an imperative programming, normally what you will do is that you will do this n forward functions here. And because most of the deep learning frameworks are optimized for both forward prediction and backpropagation, normally the statistics are kept in track of in those data structures, so they cannot be freed. And that's for the same reason that because the imperative program need to be prepared for the possible future of backpropagation. On the other hand, in the declarative program, you declare the entire forward computational graph and call a compilation function. When the compilation function basically sees the graph and it knows that all those memories can be shared in place. So as a result, you get a much less memory cost when running a declarative program normally for prediction. So normally you only need 2 copies of memory that alternates through each other. Yes?
Can you explain why the memory can be shared from different layers? Because when you do backpropagation, ABC belongs to different.
Exactly. The reason is that in our use case, we are only doing prediction instead of backpropagation. So imagine that in this use case, you only want to do prediction, and this computational graph is not about backpropagation. So this memory can be saved. That's exactly why imperative program kind of costs memory, because it wants to be prepared for the case of possibility of backpropagation, as well as the possibility of only doing forward prediction. Of course, you can optimize this program by adding special cases, like I only want to do forward prediction. That adds another layer of complication to the imperative program. So there are a bunch of optimizations that you can do for a declarative program because of the advantage of it sees the entire global scope of a computational graph instead of a local step. One example is that you can do dependency pruning. In here, this is a forward propagation step, and on the right side this is the graph corresponding to the back propagation step. So because there's addition here, you can find, and you can find that the back propagation actually doesn't depend on the value of f. So this memory can be freed as early as the forward propagation step, and we don't need to postpone that until the back propagation step. So if you only need some intermediate values of value C, you don't need even to carry out other computation as well. So this is kind of a more advanced version of dependency pruning that, yes, you can hard code them into your framework, but declarative programming can't give it free for you if you have a good optimizer. Another thing that you can do is operator fusion. So in here, because C is an intermediate variable that's not referenced by the user, and you can easily optimize that out. Say you provide a huge kernel that does the matrix multiplication plus some bias, which is commonly available in many of the frameworks. You can do this kind of operation rewriting to write this program. However, you cannot do that for the same reason, because in the empirical program, that's a possible feature that C might be referenced. And there's another optimization that you can do, for example, that I mentioned, that is memory sharing here. OK, so I've advocated so much for declarative programming so far, and it's good that many of the existing deep learning frameworks actually do follow the use case of declarative programming in a sense that you declare the neural network, then you optimize the computational structure. So why do we still need imperative programming? Or otherwise, we basically everything so far is good, and we can end this talk here. So why do we still need imperative programming? So imagine the same case for SQL in the database. We all need to imagine that you want to develop a web app that need to do a online banking system, and you have a good SQL server, say Microsoft SQL server, and it does all the good jobs for you, do all the query optimizations, gives you the result quickly, and but still, you need some front-end language like C# and JavaScript to interact with it. So why does web developers still need this front-end language? The reason is that the declarative language are kind of limited in what they can do, and there are some certain things that declarative language are not good at. Take for example, you imagine that how you can do a parameter update in declarative language. It's possible, but you do need to extend the language into some extent. For example, TensorFlow need to support mutations in a computational graph, which is not very natural and requires some engineering effort into that. Other more complicated examples include things like optimizations, like limited memory BFGS step, which requires a line search and think about like how you can write a line search program in SQL, which I don't know how to write. Maybe there are some extended language in the SQL domain that can do that. And there are other use cases like variable input lengths, which are not very easy to be described by a predetermined computational graph, and need to be used the advanced features in the imperative language to do the dynamic unrolling. So one of the advantages of imperative program is that it's deeply embedded into the host language. So also TensorFlow and Cyano are claimed to be supporting Python. Actually, when you write TensorFlow or Cyano programs, you're actually writing another program that's called TensorFlow. It's like you are writing SQL in Python. It's not like you are writing Python languages. You are writing SQL language. So when you are writing those declarative programs in Python, you're actually writing in context of those declarative programs. However, if you are writing imperative programs in Python, you are actually writing in Python because you can take advantage of all those advanced features. Like you can condition on the data set lines. In here, this is a very naive example. Say I have two types of neural networks that I like to do. For input data length that's bigger than 10, I use first type of negative architecture. And for the other input type, I use second type of architecture. If you have an imperative program, you can basically very easily do the runtime dispatching and select the path that you want. There are more complicated examples. For example, you might want to take a look at output of a neural network and decide which path you want to go. This can be very common in reinforcement learning. And on the case of recurrent neural networks, say you want to do prediction, you want to dynamically unroll your predictions, and the length of the predicted sequences is not determined in the beginning. Of course, all these things can be hard-coded in your system and optimized for specific use cases. But to support these things in a generic version, we do need some flavor of imperative programming in order to do them easily. So that's why we want to advocate for a mixed flavor. So mxnet, the mx in mxnet kind of stands for mixed flavor. We want to combine the power of imperative programming together with the optimized declarative programming. So as we all know that, as hopefully you are now convinced that the imperative programming are kind of more flexible and allows you to write whatever things you need. Say you want to insert your optimization step and your training loop. On the other hand, the declarative program can be quite powerful in a sense that the system can optimize the memory, computation, and everything in behind for you. So in mxnet, we provide two sets of APIs that are coupled together in a sense that they work together as a whole piece. So we have a NumPy-like ND array interface that basically executes as you go. That's the imperative programming part. And then we have a symbolic API that basically does the declarative programming part. In the whole, so this is an example of a basic training loop in mxnet. So what you basically do is like you write an imperative loop here, and we have a dictionary that maps the string of key input to the corresponding array. So every iteration, what you do is that you copy your input to the corresponding arrays. That's the imperative step. The executor itself is compiled from a declarative language. So you declare all your neural networks in those and compile it into executor. Then you call executor.forward, backward. This is an optimized step that optimizes for memory. And then you use the imperative step. This is the imperative step of SGD, but we can definitely put more advanced step like the variance reduction method that developed here, or other type of optimizers here. So the reason that the fact that we are able to use the imperative step actually helps us a lot in a sense that after we released mxnet, in the beginning we only have SGD with momentum optimizers, and after a few months, many people contributed other optimizers like RMSProb, Elagrad, and all these people are not original developers of the framework, which shows that mxnet is kind of easier to use in terms of these imperative programming. On the other hand, it's still very efficient in a sense that all those bottleneck parts are still optimized by those declarative programming part. Another example that's actually quite exciting for me is about the support for variable length input or variable size input in images. So recently, this is actually thanks to a proposal of Jacob, who is in Microsoft. So as you know, if you do sequence training, normally you have sequence of different lengths, and it usually corresponds to different network structure of different lengths or different shape. So thanks to the imperative execution model that we have, actually, this is quant by Xu, and he added a support of the bucketing API, which basically switches by the input length and pick different executor for execution. So each of these executor correspond to a different network for that specific input, and all these executors can share the memory. So according to him, we only cost around 10 lines of Python code, which may be a bit exaggerated, but I think I truly believe in him because this is basically a map or switch in Python, and that's all you need to support the variable length input. So in summary, in terms of programming models, hopefully you are not convinced that there are two style programming models in deep learning languages. Either you can do declarative programming that's very optimized, and engineers always like that. It's good in production systems. On the other hand, imperative programming gives you the flexibility of inserting whatever you need into the control flows and doing runtime dynamic dispatchings of your operations. Combination of these two can maximize your productivity for one reason. This is the best thing that I learned from my undergrad. That's Amdahl's law from computer architecture. Basically, it says that you only want to optimize the bottlenecks in your system. So this is the same for the deep learning. Usually, when we are doing extensions to a deep learning program or deep learning architecture, we are extending the part that we extend may not be the bottleneck of your computation, and usually we can put many of the existing pieces in those declarative languages and use imperative language to smoothly add the things we want to add and still get the maximum performance you want. And that motivates us to use this kind of mixed programming design. Okay. So now we have talked about programming models. Another thing that's very important is to try to develop a system that effectively supports these two kinds of programming models and allows to mix them together, especially in a multiple device environment. As we all know that when you have a machine, now you can put 4 GPUs into it, and if you are in a distributed environment, there are even more resources you can utilize. And it's very important to be automatically utilize all the resources to maximize your performance. So, however, it's quite painful to write multi-threading programs or concurrency programs. Although I like them very much, but it's really painful to write, especially to write them for specific cases. So one thing that we did is we have a dependency tracking engine that automatically parallelizes all our operations for you. Here's the example. So these are 4 imperative crosses of operations. And you can easily find that these 2 operations can run in parallel. And what we actually have is that we have a generic dependency engine that will track all the operations, including the imperative and the declarative executions, to train them together and automatically parallelize all the possible operations you have. Here's a more realistic example. So this is a bunch of code that you don't have to read, but basic idea is that this is a 2-layer neural network that runs on 2 GPUs, and you need to copy the data to CPU for synchronization, do the update, and copy them back. So these are the generic code of a data parallel paradigm you have. And this is a Python code that you can write actually in mxnet. This corresponds to this computational graph. And there are many interesting aspects from this computational graph. So you can find that there are computational paths on the left side that's on GPU 1, on GPU 0 actually, and on the right side is the computational path on the GPU 1. And you can do the forward-backward propagation. And after the first back propagation of the top layer, as soon as you get a result, actually you can copy the data to the CPU, do the update, and copy them back. So one of the important optimization that you want to do for this kind of computational paradigm is that you want to overlap your computation with the communication. So as soon as you get this result, this memory copy can happen, and concurrently you can do this another step of back propagation. And you can find a similar pattern in model parallelism as well. For example, in a multi-layer STM, as soon as you get the first timestamp ready, you can directly copy the result. The second GPU can kick off, and all the things can start in concurrently. However, it's quite hard to hard-code all these patterns and do those asynchronous communications. So we do need a dependency checker to check all these imperative and declarative operations. One of the key properties I want to emphasize here in our design of the scheduling engine is that is designed to be transparent in a sense that where we don't want to make assumption of what kind of operation we want to schedule. And basically, it means that we can schedule anything, including those code that aren't written by us. Okay, which Eric will give a more detailed example, actually. So, however, there are a lot of troubles when you want to have such kind of dependency engine. One of the trouble is that about memory cycling, actually, surprisingly. So here is a two dependency paths that you have two operations that depends on C and B, and then we have a memory deletion that's automatically triggered by a garbage collection. However, this memory deletion cannot happen before those operations are carried out. So this is like implicit dependency that you really need to be able to track. Another interesting example is about random number generations. So here you have two random number generations in your code. It seems that they can run in parallel. However, as if you're familiar with random number generator, usually you have to run in a serial manner, either for reproducibility, because every time you do one to the same sequence code gives you the same result, and another reason is that random number generator is a result that it cannot be shared and have to be serialized. So in order to support these two kind of operations, you really need to extend those dependency engine from an immutable scheduler, which is the technical term, but which you don't have to understand, to something that supports mutation. And in our framework, what we do is that we try to do things in an abstract way. So for all the possible resources, memories, random number generators, and all those things, we will allocate a variable or tag to and attach them. It's like a tag of your bag in the flight. So attach them to each of the resources. And when you push the operation to the engine, you use this tag to specify what resources you want to read or mutate. And engine treats the operations as a black box, in a sense that engine simply use those tags to track dependency and execute them when ready, but wouldn't actually know what's in the content of this lambda function. So all these code execution patterns will be translated to a synchronized call of these pushes into dependency engine. And you can plug in arbitrary functions in here as well, including the code that you developed here. So this is a huge picture showing how we do it. I'm not going to walk through it, but you can always read it from our blog post. We have a detailed design doc of what we did in those systems. Basically, we have a multiple dispatching queue that is aware of the read and write dependencies. So to recap this section, we really need a good dependency tracker that tracks all the dependencies if you want to build a powerful system for multiple GPUs or multiple resources. And having such dependency engine makes things easier for you, in a sense that you don't have to hard code all the data parallelization patterns. And if you want to have a model parallelism, you simply write the Python code in a serial manner, and it will execute the dependent operations as soon as it's ready, and it's ready to use and gives you the maximum performance. And it can also be used in combination with other optimizations, such as data compression, which optimize the cost of each individual operations, in a sense that such kind of dependency tracker helps you to run more things in a concurrent manner. Okay, I mentioned the two major motivations for us to build a system. We want a mixed programming model for maximal optimization and the flexibility. And we have built the dependency scheduling engine to schedule arbitrary operations so that you can make arbitrary parallelization pattern more easier. And I'm going to briefly walk through other features that might be of interest. But yeah, so mxnet comes with low memory consumption, mainly because we have those declarative optimization part that optimize memory. So as an example, one of our friends actually trains an entire ImageNet data set on a single machine with 4 GTX 980 GPU, which is not a very good GPU because we can use less memory than the existing systems, so we can fit bigger neural networks into those bad cards. It's also lightweight and portable, in a sense that it's available in all the possible languages and the major platforms, and it's also available in Windows, of course. And you can find it in all the mobile devices. And one interesting thing that we encourage you to check out is we have a JavaScript version, which means that which actually runs in your browser. So if you can open this link now, if you have a laptop, and there's an image classification demo that runs on your browser. And Microsoft do have an advantage here in a sense that Microsoft Edge actually runs, I think, 8 times faster than Chrome because they didn't optimize for the ASM.js part. But so this is really due to the fact that we make things really portable in a sense that all dependencies are minimized, and we can compile the entire project into one file and compile it into JavaScript. And this
Does the JavaScript use the same backend code with the?
It uses the same backend code, yes.
So what? Run C++ things.
Yes, exactly. So it's a technical inscription that compiles C++ code into JavaScript. But you do need to isolate all the dependencies in order to be able to do that. And this comes very handy when you run demos, for example. If you have a new model that you want to show to your colleagues, basically you can run a demo on their browser, and you don't need to have a dedicated server for whatever purposes. And it also runs on major cloud platforms. We have a built-in support for AWS S3, and I think there's an ongoing pull request on supporting Azure integration as well. And it runs on major scheduling engines such as MPI, SunGrid Engine, and Hadoop Yarn. So this is a comparison of single GPU vision task. I think a major takeaway of this slide is that also we support mixed style of imperative programming and the declarative programming. We are as efficient as all the major systems because we share all the same kernels and all the things. And mxnet is really well optimized for those inception style or residual net style architecture that have multiple paths, which gives us a much more memory saving than the existing frameworks. And we have a new optimization that's able to further optimize another factor of 2/3 using the graph rewriting techniques. And here's a comparative example about forward-only computation and forward plus backward, which answers your question in the previous, which answers the previous question about like why forward computation gives you cost less memory. Simply because there are less memory dependencies, and you can save more in the forward computation as compared to the forward plus backward computation. And declarative programming gives that for you. On the other hand, imperative programming also gives you all the power that you need to write your research code easily and ports into the productive environment. This is the entire overview of the system. Basically, it's kind of very different from an existing system because we build it in a way such that we want to have an ND-array module to support imperative programming, as well as the symbolic execution model to support declarative programming. OK, so I think I finished all the overview about the system and the general idea behind the system. Here are some take-home messages that you want to hopefully that you can get from this talk. So from my part of the talk, and Eric will give some tutorials about the detailed usages. So mxnet stands for mixed programming and maximum productivity, 2mx. And one of the important things that we do is automatic parallelism that gives you the way to powerfully use all the parallelization patterns that you can use without hard code. And one of the things that I want to emphasize is that we are open system, like Lego bricks that you can plug into various parts and plug other bricks into the mxnet. One important example is that currently we actually works as a fully functioning torch module, which means that you can take any functions in the torch and use that in mxnet. And it also balances the flexibility of the symbolic and of the declarative programming and imperative programming to give you the maximum performance and the flexibility. OK, so I will hand over to Eric for the next part of the talk.
Thanks. So Tianqi has talked a lot about MX design and its cool features. So hopefully by now you're convinced that it's a good system. And now I'm going to talk about how you can use it. So since it's a fairly technical audience, I will assume knowledge of machine learning and Python and NumPy and such. So we actually do have other front-end language wrappers like Scala, Julia, R, and etc. But Python is the most supported, and it's the language I use. So I'm going to give examples in Python. So And by the way, feel free to interrupt me. I know that some of you may have played with mxnet already. So if you have deeper questions, you can interrupt me anywhere to ask. So first, the symbolic graph. Is the Mac working? Okay. So first, mxnet is the basic usage is symbolic graph, and symbols are basic units of computation, and you can define symbols like this with a function call, and a symbol has input, and it has name and a number of parameters, like how many hidden units this fully kinetic layer has for output. We also provide, this is like the cafe layer, and it's a coarse granularity symbol. We also provide finer granularity symbols like plus, multiply, and you can define it with the FC1 plus 1 assigned to FC2. So, and that's actually executed in the symbolic engine instead of just a imperative clause. And then graphs are defined by composing symbols. You first have a x, which is a variable, which basically serves as a placeholder for your input data. And then you feed it through the network. You have fully connected activation and softmax. And then this will give you a network which can be instantiated with memory to give an executor. And here we use simplebind, which allocates all the memory buffers for you. You can also call bind without the symbol and provide your own arrays as buffers and gradients. And everything that you don't bind, if you use the bind method, everything you don't bind won't be computed. If it can be omitted, they won't be computed. And like if you don't bind a gradient for an array, it won't be computed and you won't be able to see it. So anything that you want as output, you have to bind it. Otherwise, it will be optimized out. So after that, these are basically works pretty much like NumPy arrays with some limited feature. And you can assign to the input, which is the data, and then you do a forward and then do backward.
So after you declare a symbol, and then you do some imperative, so-called imperative programming on those symbols, it's still declarative programming, right? So because you still program on the symbol,
Yes.
so it cannot be called mixed program. It's still programming on the symbol.
Well, so this is a symbolic graph. Here it's bind, and then you can go forward and backward to it. These are two black box symbolic computational graphs. And in the middle, you can do anything you want with it. So the output array is just a ND array. And you can say, take that, feed it to a CRF, and do some inference in the CRF, and then take the gradient back from the CRF, and then feed it to the backward. You can add arguments here.
That is after you run forward, means you call the executor to execute.
Yeah. So
Yeah.
The executor is actually declarative executions.
Yeah. So the
So in other frameworks, you can also call feval or something to get the values, and then you can feed those values into whatever.
The difference is that in most of frameworks, after you call eval, you get a value in NumPy array, and you do need an imperative GPU arrays to support all those operations. The second difference is that all those operations need to be parallelized, in a sense that in the existing framework, all you do is that you take that NumPy array and you do the update. But all those operations are not parallelized, and they are not aware of the dependency. So those imperative parts are actually acted as a fragmented part instead of a whole piece.
So basically,
I think this is mainly just a library function call in any language. Well, why is it different?
Well, so basically, the forward,
Forward is function call.
yeah, it pushes.
Result, right? You call forward, you get result.
Not really. So the forward is, after you compile this graph, the forward actually pushes a whole bunch of operations to the engine, and then it returns without waiting for them to finish. So you pushed a whole lot of stuff into the engine, and then say the network has 10 branches, and you have 10 outputs. The forward immediately returns, and you can take each output and do anything you want with it without waiting for the other 9. You see what I mean?
In a sense that all the things are automatically parallelized and executing in a synchronized manner. So that
but that is still, the parallelization still happens inside the library, right?
no, it's not happening. So it happens inside the function call as well as outside the function call. So after you call a forward and backward, you do a parameter update. That parameter update can be parallelizing together with those forward and backward calls. So as soon as you get a gradient in a backward call, the parameter update will happen. So that's the major difference between like a serial execution and the automatic parallelization.
But parallelization still happens inside your library, right?
No, it happens in Python.
Parallelization happens in Python?
Well, it happens in the engine, but it's issued in. You can issue everything in Python.
Yeah, basically you issue everything in Python in an imperative manner. That's the difference between. So most libraries allows you declare a graph and you do whatever parallelization optimization on that graph. But most library doesn't allow you to do parallelization over different type of graph execution. For example, you execute a graph, get a gradient, you do the parameter update. That's a different operation. Most library doesn't allow parallelization between those two operations. Because if you want to really support imperative operation well, you do want to be able to track all those dependencies and parallelize all those operations as a whole piece. Because all these operations are also run on GPU, and they need to, for example, the parameter update need to be done as soon as you get the gradient in the backward step, instead of waiting all the backward step to finish.
So basically here, you have these network layers, and each one has a few parameters. After you do a forward, you can do a backward pass. Then it will, since this is a linear structure, it will execute from this one to this one and then backwards. And the backward actually returns immediately after it pushes all the operations into the engine. And then when you do the update, you call update on each parameter. And if this is just a normal function call, you would need for the backward to compute the gradient for each of the parameters before you can do update, before it returns.
Asynchronous or not, right? You can do a function called asynchronous that return immediately, right?
Yes. Yeah, but then you need the dependency engine. So basically, that's why the dependency engine is good, because it registers all the read and write operations on each of the parameters, so you can issue everything without waiting for anything to finish. It will get automatically dispatched when it's ready to be run.
But since the computing device is limited, okay, and when you run some computation on the computer device, that device is occupied, then you cannot run another computer.
Well, so
So based on that, you have the limitation of computing device. The only thing you can actually parallelize is memory copying and some computation, right?
So there are two cases. So first, if your network has multiple branches and some layers are small, running that layer doesn't occupy the entire GPU, then if you can run 2 branches in parallel, it gives you a speed up. The other is this extends naturally to multiple GPUs. You can easily do model parallelism across multiple GPUs.
Yeah, but we discovered this in the past. This typically will be slow down your overall computing significance. Every time when you copy information between GPU devices or GPU CPU.
Well, you need to.
That's why you need dependency engines.
No. This is what I mean. Dependency engine itself is not enough.
Well, you need a special model structure for that.
Not just dependency engine.
Well, yeah, I know. So basically, if you just take a VGG network and you put the first convolution on one GPU and the second on the other GPU, it won't work very well. But if you have a more decoupled structure, it will work better. Say, these days they have the two-stream video recognition network that has one stream for RGB, the other for optical flow, and then the two stream merge on the top. Then you can easily parallelize the two-part on two GPUs.
Right, but you still, if you want to get optimal speed up, you still need to have some human hint to decide how you want to parallelize or where you want to run each branch.
Well, you just need to say which symbol should be allocated to which device.
So you basically tell the system.
Yeah. You say which symbol goes to which device.
Okay, then I don't see any benefit other than parallel between computation and the memory card, because you still need to human to decide exactly which one to compute. It's the same as other toolkits basically. You can also do the same thing.
Well, this is
two separate branches. You can compute each one independently on different GPUs, and then just have a glue at the top. So it's very similar. You can basically easily implement same thing on other toolkits as well.
well, yeah, but that requires manual coding for each specific case. And as soon as you get to 4 GPUs with crazy network structures, you'll find yourself writing like hundreds of lines of code for each specific network.
No, that's not true. Actually, once you have more than 4 GPUs, this kind of organization typically will slow down your things significantly.
Well,
so that's why in all our current implementation of cross-machine or cross-GPU parallelization, we have some. We need to use some other techniques. Cannot just use. In your case, this is per mini batch parallelization across multiple machines, right? Mm-hmm. This typically will be very slow, especially when you cannot increase the mini batch size larger. Then this will be also a problem. So this. But I understand what they are talking about now.
okay, yeah. So one thing is the Pascal GPUs are coming out in probably half a year, if NVIDIA keep up their promises, and they advertise for like 10 times faster GPU to GPU communication with NVLink. So I think maybe it will probably get to a point where inter-GPU communication is similar in speed to within GPU communication, because they have these 3D memories.
For example, in our case, we can reduce memory consumption transfer by 32 times by quantizing the gradient.
Yeah, well,
even doing that is not enough. You understand? Even quantization by 32 times is still not enough.
I think it depends on your network structure. It depends on your application. For some applications, it doesn't work. For someone, it will.
Yeah, but basically, I understand.
Yeah,
I don't understand because you're saying that data parallelism doesn't work and monoparallelism doesn't work and one-bit gradient doesn't work. What then won't work?
No. One bit works if you can increase the mini-batch size to very large.
So that has nothing to do with their toolkit. You can choose any mini-batch size you want for any toolkit.
No. If you increase the mini-batch size too large, then your final model's performance is bad.
But I don't see what any of this has to do with the toolkit. This toolkit supports monoparallelism, data parallelism, and it could be one-bit gradient stuff supports. I don't see what.
No. What I mean is that even 1 bit is not enough. So what he said is, as long as they can improve the data transfer between GPU and CPU, it's enough. I mean, this is not enough. That's why we have some other algorithms better than 1 bit quantization to actually make this work. In all those experiments we basically, this kind of parallelization is not enough. This is what I want to
Yeah,
say.
yeah. What don't want to say is that you need to increase the minimum size dynamically to saturate the communication channel so that you can gain the benefit. So this is the whole point. Like you need to increase the minimum size.
So,
But I have a related question. But actually, I'm actually like the dynamic scheduling for operations and for memory. But what concerns me actually is a table that you had in the earlier part of the talk, that you are comparing your performance to something like Torch. Okay. So Torch is kind of the other side of the spectrum, where the researcher or developer is like building all these optimization by hand, and the kind of the argument is Torch should offer the flexibility, but mxnet and other symbolic or like declarative programs will offer the optimization.
Yes.
But in these tables, I didn't see this huge difference in terms of speed ups or memory. This is one part, maybe because all these networks are standard and everyone's using CodeEN, for example, for convolution and so on. But the other part of the question, like if you have some into like kind of experiments, like for something like machine translation models or like deep LSTM language models, where you can do model parallelism and show difference if you have some benchmarks. The other part of the question is, if I would do the standard stuff, all the toolkits are the same, but for the non-standard stuff, maybe an imperative program would be easier to work with rather than a declarative program. And if the difference in speed and memory is not that big anyways, why should I go for declarative programs?
Basically, for the standard networks, people working on Torch put a lot of engineering efforts to optimize them, and so basically in the end they get to the basically similar optimization as we do here automatically.
Like bare layer optimization. Bare operational optimization, like they have.
Yeah, well, so like for example, for the ResNet, the network is so big and so many layers that it doesn't fit into memory. And so what they did is, in the backward pass, they take a gradient blob and walk it down through the network, so that you don't need a gradient blob for every layer. We do this automatically, and we do many more optimization for that. But for Torch, either you need to, as a user, you need to code the optimization for each network. You need to figure out what to do, and then you need sometimes significant change to the infrastructure to do that. You certainly can, but it's kind of too much trouble. Otherwise, you can also add a gazillion options to the standard library so that you can turn on each one and turn on each optimization, but it quickly becomes unmanageable.
So this actually means a kind of follow-up question. So what you're saying is that for Torch, they did the co-share, what you called co-share by hand, right?
Yeah.
So did you try to run ResNet on the same kind of memory, with mxnet on the same kind of GPU card with the same memory limitation? See if your kind of automatic co-share would be runnable, or would it run out of memory?
I personally haven't, but we have people who have.
It will run. It's the 6 gig card, I see.
Yeah. So basically, we did most of the memory sharing that you can do automatically, and so this requires less effort when you are exploring new network structures.
Question. Your loss layer is not separate from the activation layer, so that softmax output means softmax loss and activation.
Yeah.
So then how easy it is to change the loss to an arbitrary loss that we want to define in mxnet?
You can do it with. It depends on how complicated your loss is. We have softmax activation, so that's only the activation instead of the activation with and loss attached to it. And you can do anything on top of that by either creating new symbols or composing existing ones.
A question along that line. So you couple the softmax activation and the loss together. So after you train a model, how can you use the model at test time?
Well, at test time, you just don't call backprop, and then it will work.
But even if you don't call backprop, you still call forward, right?
But forward doesn't require a label, so.
So that's a special symbol in the forward. It's not output the loss function value. It's output the activation value actually. So it's
so basically like spatial casing or
no. So in all of our output layers, we don't output the loss. The loss is computed separately, and all these just output whatever it's supposed to output instead of the loss.
Okay.
The loss is computed separately if you want it.
But in this case, how can you connect the gradient coming from the loss to the model?
The gradient actually doesn't come from the loss. So imagine you are doing softmax. You have each node you have a activation, right? The gradient is just that -1, right? So the gradient doesn't require you to explicitly compute the loss. So you don't need to.
But sometimes the loss function might impact the way that you compute the gradient.
Well, for that layer, you can compute the loss. So in this case, you don't need to.
So is there a way to, if you wanted to chain different graphs together because like you wanted to do a dynamic network?
Yeah, exactly. We're going to talk about it in the following slides. So I want to talk a little bit about naming. So in mxnet, every symbol and every array in the symbolic graph has a name. And the names are not arbitrary. So we have certain name conventions that can impact behavior. So you can create a variable placeholder by declaring a variable. And all the other output arrays and unnamed input arrays will be named by symbol name and default array name. For example, FC1 weight, FC1 output, which didn't appear in the previous slide, they will be named by default. And in the default model and updater, you don't have to use this, but if you're just using standard feed-forward neural network, probably this will make it much easier. If you're using this, all the arrays that ends with weights will be treated as weights. They will be weight decayed and initialized to weights, and the biases will be initialized to 0 and won't be decayed. And data blobs from the data iterator will be copied to the blob input arrays with the corresponding name. So these are like variable names in your program that it's not just for display. It's not arbitrary. And so I just want to quickly mention that I/O in mxnet is different from TensorFlow and Caffe in that in TensorFlow and Caffe, it's just a layer in their graph. It takes nothing and spit out data. But here we separate the computation graph from the data iterator because we want to make the forward and backward cleaner so that it acts as a function that takes input and gets spit out output. So these are actually separated, and during runtime, you will be copying the data into the model, the executor. And we provide a number of default data iterators like ND array iter, which allows you to use NumPy arrays as input. And we also have image record iter for ImageNet and other image-based, and we also have mxnet iter. And you can easily create additional data iterators in the front-end language, like in Python, by subclassing the base data iterator class. Mm-hmm.
Do the data iterator support shuffling, or do users have to shuffle the data themselves?
Well, it does some local shuffling, but not global ones because it can be very efficient on SSD. So, so basically, we take 1,000 examples, shuffle that, instead of take the whole data set and do a complete shuffle.
So you read log by log?
Basically, for this iter.
That's also like a random reading of random blocks. So that's a global random block shuffling and local shuffling.
Okay.
So it's not the entire shuffling as you would do with a one array, because it can be very inefficient for like HHD disks.
It's specific to just a few iterators.
It's specific to
every data iterator.
well, so this is just in memory, so you can do any shuffling you want, and this is on disk. So for large image data sets, so we only do local shuffling and block shuffling. And this, I think, is not shuffled because it's just a example as like it makes it convenient to show MNIST results. And when you're subclassing this and creating your own data iterator, you can do whatever you want.
But as a user, how do I know which iterator supports shuffling and which one doesn't?
It's in the document, I think.
Okay.
So by the way, does it handles sequences nicely or not?
Yeah, recently we added that. We do bucketing for sequences, which I will explain shortly. So after you have the data and the graph, you can train it pretty easily by first creating a model object. You specify the context you want it to run on. This is GPU 0. You can feed an array here, GPU 0 to GPU 4, and it will parallelize that for you. You can also do, so here is an example. So if you use VGG or GoogleNet, which especially GoogleNet, which has very few parameters but has a lot of computation, we on single machine with 4 GPUs we get basically linear speed up with multiple GPUs. So and all those are just automatic. You don't need any coding for that. I will also cover recurrent networks and more complicated examples later. And so since mxnet the executor will optimize everything out if you don't need it, this can make debugging harder because sometimes when your model are blowing up and you don't know why, you want to print the intermediate gradients or weight arrays during the training to see some of them are doing weird things. To do that, we provide a monitor class that hooks into the executor, and immediately after each array is computed, we push another operation into it and saying that take this array and compute some statistics on it and return the statistics. So after you create a monitor saying I print every 10 batch with this statistic function, this is just a standard deviation, and I want to compute on everything, on every array that matches this. This is regular expression matching, and sort the result based on name. Then you can bind the executor and install the monitor to it, or you can provide the monitor to the fit function, and you will see these statistics printed out every 10 batch.
So I have a question on this. So I think debugging is very important for this a lot of things. So do you also, for example, can I step into to have some breakpoint or whatever, some other?
Have what?
For example, if I'm particularly interested in a certain node and its value, so I want to look at it and then print the value, and then you have such.
Well, here you can return arbitrary things, and we will print it for you. So whatever here, but remember that this is pushed into the engine, so you cannot do async. You cannot do blocking calls here. So this just do the basically any async arithmetic computation. Just don't call as numpy here. So basically, don't take the ND array data and try to copy it to the Python front end. It will be copied and printed later, but don't copy it here.
Also, if I want to do gradient checking, so you have code already, right?
Yeah, we do have gradient checking.
That's in Python, so it's much easier.
Okay.
Yeah. So and also this does hurt performance because you're computing all this stuff and it's blocking the computation each step to compute this. So only use it when you need it, and probably set this to a bigger value. Okay, so we built mxnet with the idea that it should be a open system that's easily extendable. So we already have some examples of that. We can call torch tensor functions. So basically ones or SVD or all those torch functions with mxnet ND arrays, and it's executed in the engine asynchronously. So it's pretty transparent. It's as though you're just using mxnet's own functions. And we can also integrate torch NN layer into mx symbolic graph. So you can take one torch script that defines a layer. It has forward, backward, and gradient. And you can embed it into the mxnet symbolic graph as one symbol. This allows you to migrate any existing work in Torch you have to mxnet pretty easily. So basically, when you develop new algorithms, you pretty much define a set of new layers that you want to use, probably 2 or 3. You can just port it into mxnet, and you won't lose any existing work. And we are also working on Caffe integration. It's harder because Caffe doesn't have a full function scripting interface. So we need to fake Caffe's headers and like compile with it. It's a lot of hacking. But with Torch and potentially TensorFlow, it's pretty easy because they have this scripting interface. So here we show how you can call Torch tensor functions. They are provided under mxnet.th module, and you can create random arrays, and you can call arithmetic operations on it, and you can create multiple ones, and then do arithmetic computation on it. And these are all async. So when you call this returns immediately, and all the execution happens in the engine. You force synchronization whenever you take this output and try to get it from Python as numpy arrays. So they just take a mxnet's ND array data structure, which is similar to NumPy. A lot of time it can be used with NumPy arrays transparently, as if they're NumPy arrays. And all of these are pushed into the engine. Here we show how you can use Torch NN layers as mxnet symbols. So basically, these are just like any other symbols in mxnet. You have Torch module for the normal layers, and you have Torch criterion for the Torch loss layers. So basically, the Lua string is an initializer that it's a Lua command or function that returns a Lua object representing a neural network layer. So after you construct this graph, it works pretty much the same as any other mxnet graphs. but this allows you to migrate existing work. But since torch is imperative, we cannot do any memory optimization with it. So these are not memory optimized. Anything will be there and won't be freed. Unless you're only doing forward, in which case we know for certain that you're not going to call backward on it again, and it will be freed. So if you can use mxnet layer, if you don't have mxnet layer for that, call torch. So here we show how you can do custom training loop. This is more advanced, like when you are doing something other than feed-forward neural networks. Say if you have a fully convolutional network that operates on different size images, and you want to do the spatial pooling thing and generate different number of output from each batch, you can do it with your custom training loop. And a basic loop basically looks like this. You take a symbol, you bind it to create an executor, and then you take a data iterator for the number of epochs, you reset it, and then enumerate batch from the data iterator. And for each batch, you load the data to the executor. This is basically a bunch of assignments. And then you call forward and then backward. In the middle of the forward and backward and before and after, you can do anything you want with the output, like using a CRF to it, or take this executor's forward output and feed it to the next executor's input, and then call that executor's backward and feed the gradient back to this executor's backward as argument here. This here, it doesn't have any arguments because the mxnet neural network has a loss layer at the end, so it doesn't need gradient input. And then
How does it know which ones are missing from the? Is it basically the terminal nodes in the graph? Like if it tries to execute that and it's missing, it'll throw an exception at runtime or something. Like basically, you know what I'm saying? Like there's some nodes that are in the DAG. Like there's some nodes that don't have any. In this scenario, there's some nodes that don't have any thing coming into them, right? But you still, and that's what you have to pass in the partials with respect to that output for those guys. Do you know what
so here whenever you bind, you will need to provide every input and gradient to that. If you don't provide, they will be optimized out if it can.
I see.
If they can. So if you don't provide a weight, it's pretty bad. It's going to be a random.
Well, let's say you have a softmax output, or just let's say you run a recurrent neural network over a sequence. You take the final hidden state, and then you want to pass that as input to another network, right? Mm-hmm. Then you need to pass back the gradient with respect to that final hidden state. Mm-hmm. Where do you say that? Like, where do you tell the network, hey, I'm going to do this? Like, do you have to bind a variable to that final?
The backward of the other executor will give you gradient for every input.
Right.
For every input you require it to. Others will be optimized out. For the things you have, you can take that, assign it to the head grad here. You just
and
take
the graph optimizer, the first thing knows that one's missing, right? Because if you didn't provide that, you couldn't.
Yeah. So if the final layer is not lost, it will need head grad to backward. Okay. If you don't provide one, it will throw an error.
So it assumes that whatever in terms of the actual DAG, whatever the final thing is going to be the one that you provided to.
Whatever you bind on is.
Yeah. So you need to specify which one you want, and then it will be the head grad, and then you need to assign to it.
Okay.
So are you overlapping the I/O with the forward backward update somehow, or do you like stop each time it goes next? Is there like some internal queuing of the iterator?
It's done by the dependency engine.
So all these are scheduled. The forward will return immediately, and this will return immediately. And the updater also push the computation of the momentum and modify the weights, and these are also into the engine. The only thing that's synchronized is the metric update, because you need to compute the metric and print it out. So this is synchronized, and this is synchronized on the output, so it doesn't depend on the backward. So as soon as the operations in the forward finishes, this will return, and then we will start the next batch. So the backward could be still running. We are already doing the forward for the next batch.
Right. So when you are blocked on update, you're not doing any I/O, right?
Update doesn't.
Waiting to get the next. That's
that's what data iterator do. It does prefetching.
Does prefetching.
Yeah.
Prefetching.
So you have example of the fancier things that you put in the middle of forward and backward.
Not in.
Something, for example, you have CRF.
Not in the slides.
Okay.
But it's basically pretty easy. You take these outputs. These are just arrays, and you do whatever you want with them.
So that output is output from the forward. Okay.
Yeah. And backward is these grad arrays. So as I said, you can connect multiple executors, and you can insert some imperative computation. And we also have data parallel executor manager that allows you to easily do data parallelism across multiple GPUs or across multiple machines.
So do you have a way to, for example, I'm interested in just look at a particular frame. Do you have that way?
A particular.
The gradient of particular frame. So I'm not interested in all the frames. I'm something like the second frame or third frame.
So you
frame, you mean layer?
The time. So you usually.
Do you have like a video stream? Or?
Yeah, for a certain stream. Like
so basically, you don't bind whatever you don't need, and they will be optimized out if you need to compute them. And if you don't need to compute them, so if they are not in the middle of other things you want, you just don't compute them.
Even for samples inside the sequence?
Well, it depends on how you define your graph structure. Basically, it's a DAG. Whatever that you don't need, say you need the output here, so whatever that leads to here, which is an output that you don't need, this branch won't be computed if you don't bind this.
So probably the question should be asked this way. So if you have a sequence as an input, for example, in recurrent networks, we have sequences. Are you treat the whole sequence as a unit, or you treat each sample as a unit in your DAG?
Well, you can do either. So basically, if you treat each sample as a DAG, then you need to, in Python, feed one to the next. If you bind them as entire DAG, then you just take the input and then get the output. Whatever that suits your application.
So maybe no. So this will be different. For example, if you treat this as a whole sequence, in your whole graph, you probably only have, for example, if you have used a recurrent connecting at third hidden layer, you can do batch computation for the lower layers and upper layers, but not that layer. Is this handled in your tool or not?
I don't quite get what you mean. So
that's a specific application that you can run in Python, basically.
So you need to write this in Python and to do those batching by yourself, basically.
If you need that pattern.
No, this is not bad because this can be optimized inside the engine, but you are not doing that right now, right?
What exactly can be optimized? So you're saying.
If you have a recurrent network. Let's consider the simplest recurrent network where you only have a self loop at the third hidden layer. If you have 5 hidden layers, you only have a self recurrency at the third hidden layer. If you treat each sample as an independent stub, you need to unroll the whole graph into a very big DAG. And you compute each sample independently. So you can parallelize, but each one is a very small computation, so it typically very slow.
That's where the dependency engine come in. So
what I mean, this is very slow. A better solution is to compute everything below the third layer as a huge batch computation, so it's very efficient. Everything after above that is also a whole batch, it's also efficiency. Only the third layer, which has the recurrent connection, you need to compute sample by sample. This cannot be.
Well, the symbolic graph doesn't enforce batch size across symbols, so you can change the batch size wherever you need. And so the dependency engine, if you bind every executor for each time step, it won't. So the forward will return immediately after it push all the execution into the engine. And then you can directly use the output, although it haven't been computed, you can directly use the output and feed it to the next executor. And the dependency engine will schedule everything for you. And you don't need to do any synchronization manually.
I'm not talking about synchronization. Probably we need to talk about.
I think this is too much of a subtlety. I think I know what you're talking about, but I think it's a very subtle issue that I think it's hard to explain, right? Because unless you drew it out, I think we could talk about it after, right?
Yeah, we need to talk this stuff.
So bucketing. Tianqi already talked a little about how we are doing bucketing for variable length or size inputs. So basically, if you have a fully convolutional neural network on variable image sizes, for example, for image for detection, you can allocate multiple executors and have them share memory so that you are not going to call them in parallel. They share memory, and your memory cost will be equal to the maximum cost of the maximum executor. You can have one executor for each image size, and you can cache them and whenever you get an image, you put it into the corresponding executor. Question?
Yeah. What's the overhead of spinning a new executor?
If you are sharing memory, it's pretty fast. We didn't do exact computation, but it's basically some graph search. So basically some DFS search on, say, 100, 200 node graphs. We need to compute the dependency structure.
For each mini batch?
No, it's done ahead of time. So it's
no, for each executor. If every mini batch have absolutely a new size, so no two mini batches share the same input size, you will need to create one for each.
But isn't that usually the case when you bucket a mini batch? Well, you have one bucket for each mini batch.
Well, you have one bucket type for each mini batch, but the cost is done ahead of time. So you define how many buckets you have ahead of time, and then you assign it to one batch. But still, it's a one-time cost, so it's not really anything.
No, but during the computation, do you do them one by one, or you do everything in one batch, in one kernel operation?
Well, it depends on what you want to do. So one kernel feed-forward cannot operate on different sized images, right? If you have within one batch different image sizes, you will have to do the maximum. You will have to make the batch the maximum size and then pad the smaller images. Because like GPU doesn't work that way, you can't do the forward.
You wouldn't do from 1 to 50, you do like buckets of 5 or 10, right? So that
You can assign images with very similar size to each batch and save some overhead.
Yeah, actually in CNTK we group everything together. It doesn't matter what the size is. So you can use just launch as one. Actually, total two kernels: one for computation, one for post processing.
But that's only for the speech cases.
No, not just speech, everything.
Well, so suppose you have two images. One is 400 by 800, one is 200 by 400, then your kernel will need to operate on 400 by 800.
No, you can add stuff. You can basically do padding stuff.
Yeah, that's what I'm talking about. So if you have images with variable size within a batch, you have to pad the smaller images to the larger ones.
Yeah, this is what I asked you. So are you doing this together to batch as much things into one kernel operation, or you actually run this as a single operation multiple times?
It depends on what behavior you want in Python. So it can be done within like 10 lines of Python code. Depends on what you want. If we find that most people want some specific thing, we can add it to the library. So
I have a question. So maybe we can talk offline. So we Jacob may also know that. So we have this attention model. It's not only the input that is variable length, but also the output is also variable length.
Well, it
can be. So how do you do this?
It doesn't matter. Each bucket only have a fixed network structure. It has a fixed number of input and output. Say your network can be like 10 input, 20 output, 5 input, 10 output. You just create a bucket for each possible case. Hopefully.
The point is that I was the one who pushed for this. That's why I'm debugging me. And thank you guys for doing it. But is that you can do any sort of weird graph you want. And it's just a disjoint graph, right? So in this case, the attention graph says every target connects to every source. And so for the buckets from size 40 to 50, you have you have this one target connect to 50 things. For the bucket from size 30 to 40, you have it connect to 40 things. That's very difficult to do in the style of declarative, like the CNTK style, where you don't explicitly unroll the loop, because then all of these cases like one to many, like it's fine for feed forward and bidirectional LSTMs, but once you have things like, or something like, let's say it's a parse tree where for a sequence of length n, the actual graph is a parse tree, a complete binary parse tree of length 2n, right, where it's the parse tree fitting up. Doing something like that in a simple like a language of meta language saying how you want to unroll it is not really possible. But this method just lets you define this graph, this graph, this graph, and this graph, and then this is the one I actually want to use at runtime.
Yeah, so basically you can have any number of graphs, and they can be totally disjoint, and they just share GPU memory, and there won't be any synchronization because they share the same ND array, and that's scheduled by the engine. So you don't need to wait for one bucket to finish to start the next one. You can just go ahead and do it. So also, if you find yourself in need of new symbols that's not present in mxnet, you can create it in multiple ways. So first, we have basic arithmetic computations. You can just compose those and get your new symbol. Or if that doesn't work, or you want more efficiency, you can do a symbol in C++ code by writing CUDA kernels. Or we have this mshadow library, which is similar to eigen. It's basically a templated matrix library, and you can write those, and it will be able to run on CPU and the GPU. You can also define a symbol in front-end language in Python. It's a little less efficient, but it's much easier to write than C++ and CUDA code. You can just take the ND arrays and get NumPy arrays to Python and do whatever you want on it and then feed it back. We also support writing CUDA kernels in front-end with NVIDIA runtime compilation. So NVIDIA has a NVRTC library that allows you to compile kernels runtime, and we can compile kernels for ND arrays runtime. So we also support writing layers in Lua with Torch and then call it from Torch module. So there are a number of ways you can do it. And thank you. So that's my talk.